welcome to our podcast, Spacecast 101, and I'm Manav Verma, your host. So, today our guest is Mr. Ram Mohan sir, a celebrated amateur astronomer and a very close member to Dhruva. So, a pleasure to have you, sir. Would you like to speak a few words about yourself?
Good morning, everyone. This is Ram. As Manav already introduced, I'm an amateur astronomer. That's one of my passions and hobby. As a profession, I'm a software architect working for Hewlett Packard.
Okay, so now let's get started. So, would you like to introduce about your projects and what exactly you're doing in relation to astronomy right now?
Okay. From the point of view of what I'm trying to do in astronomy is that I have I have a rooftop observatory which I have put together at my home in Bangalore. And this does host a few telescopes, which is for viewing, then for taking pictures, astrophotographs. And then I'm also working on building my own radio telescopes where I also observe the sky in the radio band. And then I am also a keen student and also doing some research on ancient Indian astronomy as well.
That sounds fascinating. So, now, sir, if for our audience, if you could introduce the entire methodology of how the astrophotographs are taken, or could you provide us with a flowchart? Like,
Yes. Okay. Now, from the way we start doing astrophotography, just to give an introduction of what that is altogether, is astrophotography is an art and science of taking pictures of celestial objects. And why I say that it is both art and science is that from the point of view of science, we need to understand what this whole object is about. What is that you're trying to take a picture of? What is its physical characteristics? And is it a planet? Is it a star cluster? Like what my background is right now, which the picture is about a star cluster. And then we'll have to understand whether if it is a planet, then we'll have to find out, or we need to know what is this planet, what is the rate of its motion, and how fast is it moving? Is it in the right opposition? Is it in the right conjunction? All these means that how far right now is it from the earth or the sun, and how will it appear when I take a photograph of that. And each one of them will be going through their own phases or cycles. Okay, when we talk about planets, they go around the sun. That is all a well-known fact now. So, how far in the orbit is it from the point of view of where you are the observer from the Earth, and where is this object? Is it right in front of you in terms of is it coming in between the sun, or is it moving away from the sun? So all these matters, because when it just tells you that how better the picture will be, and what you have to observe, and what you can observe from the picture. So that is planets. And then one more thing about planets is that, which we also all understand, is they move faster when compared to a star field. So when you have a star field behind, when you have planets, and they move much faster. And some of them, like Jupiter, say for example, though they move kind of slower, but the rotation on its own axis is very, very fast. So in almost a matter of say 8.5, 9 hours, you can see one full orbit rotation on its own axis. So when you are taking pictures of these planets, we need to use very, very high speed cameras. Okay, so the way we take pictures of planets versus the way we take pictures of stars, or what we call as extended objects, or it's also known as deep field or deep sky objects, are totally different. So we need to treat them totally in a totally different way. The equipments also differ from the point of view of the cameras that we use, and we use very, very high speed special cameras for taking pictures of the planets. And there are different set of imaging equipment for taking pictures of star fields. So the imaging equipment differs because the way these objects are behaving in terms of their rotation around their own axis, or the way they move in the star field and everything. So that is where the science comes. And then when it comes to the extended object or deep field or deep sky photography, we need to understand whether it is an emission nebula or it is an absorption nebula, because the way that the whole clouds are made up of, what does that contain? It will have hydrogen, it will have oxygen, it will have sulfur. Now, each one of these elements give out a different color in there when you capture the light. So, hydrogen most of the time, or almost always is either pinkish or deep red, hydrogen alpha, hydrogen beta. And then oxygen in its ionic form is most of the time bluish tinge. And then there is also we have sulfur coming in, which gives you the yellowish color. So we have different elements, and these are fundamentally what the stars are made up of. So we need to understand all them and then plan the whole event, taking pictures. And then we have to frame them. We need to make sure that they all look good. They are somewhere in the center when you take pictures. And for taking deep field photography, each one of those pictures take almost 5 6 days to complete. One picture takes almost 3 4 days to 5 6 days to complete. It's not that you're just sitting there one night and you take a few pictures and then you have no. To get a better resolution, you take 5 6 days to complete. But in case of planets, what will happen is that when you take a picture using a very high speed camera, high speed when I'm talk about here, we are talking about 120 frames to 160 frames per second. They are very high speed. The normal DSLR camera or any movie cameras that we use to take most of the moving images of what we do see in the everyday cinematography or anything, they're anywhere between 25 to 35 frames. Now what we use is 160 frames. Now you can imagine, so they are entirely different equipment. And when we take such equipment and even a 5 minute exposure, which will have almost 15 to 20,000 frames, will run into 6 to 7 gigabyte of data. So the way you treat once you take a raw data, then you need to stack those 60 to 70,000 frames, sometimes to some 10,000 frames, 5,000 frames. It depends upon the quality, and then you build one single image. This is a lot of post process which happens in both cases of planetary imaging and the deep field imaging. So, we take exposures of it goes on for hours, and then you all assimilate, you accumulate, you stack them, and then you start getting a lot of resolved pictures. So it's a process.
Okay, so on that note, well, I now you've mentioned about two different kinds of photos, well, optical and radio. So, well,
Mhm.
could you elaborate on the differences between the two and how they work?
Okay, now when we start talking about radio astronomy, the way that it works is a bit different than optical. Optical, of course, is falling in the visual wavelength band. Both are electromagnetic signals. Uh, one is a visual band where you can see the light which is coming, but in case of radio, you don't really see the light which is coming. It's still an electromagnetic wave. It is just that you don't see them. And the way radio astronomy works is the front end telescopes are just antennas, and these antennas are built with a specific purpose in mind, and we nomenclate them as telescopes. It's because that's what they're trying to do. They're trying to gather signals from radio sources, known radio sources. One of the most common known radio source is the sun, of course. So it radiates in almost every known radio band. It's a very great radio source. And then we have Jupiter as one of the planets, which is a known radio source. Once again, Jupiter, along with its moon Io, is a very well known radio source. Um, then when we start moving into the once again the deep field, then we have the Milky Way. Milky Way core is a very well known radio source, and there are many other radio objects, right from Cygnus, Taurus, Orion, Sagittarius, um, Scorpio. All of these are very well known radio sources. And then of course there are also certain galaxies and everything. So they all radiate in a different frequency. It's not that each one of these objects send out radio waves in the same frequency. So we need to build different telescopes to observe them, to capture the pulses and signals from them, and to analyze.
Okay, so well, now about the equipment that you use, like the antennas, the software, the other kinds of filters that you apply to your telescope, could you
Hmm.
elaborate a bit on them?
You mean the radio filters?
Yes, I mean you could elaborate on both. We'll be happy to learn more about them.
Okay, so visual filters are a bit different than radio filters. Okay, let me just. Can I share my screen and show some things for you?
Yes, sure, sure.
Okay, just hold on a second, please. Let me just share my screen.
Yes, sir.
Okay, now what you're trying to see there is filters. which are there, different visual filters, which I just try to explain. Now, these pictures here, let me just put the pointer options there. In this. Okay. Now, this filter here, which you're trying to see, is a solar filter which is put in front of a camera, a normal camera lens, and this is used for viewing the sun. This is a solar filter. The same way, you can see another solar filter which is put in front of the telescope to observe the sun. And and on the left hand side, you see a planetary filter. So when you start imaging planets, what you try to do is that we are imaging at very very high focal length. What it means is that you are trying to zoom towards the planet as much as possible. So we are looking at a zoom ratio of almost 250x to 300x, which is very very high zoom. And in terms of focal length, it will be anywhere between 4000 to 4500 millimeter focal length. So when we start looking at objects at that high zoom, what will also happen is that the Earth's atmosphere, is boiling. It's just like a it has got very high dense gases which are at very high temperatures up there in the Earth's atmosphere, and then they also boil. So when it's just like you're looking through a steam, you're looking through an object at the other end, and then there is this steam which is emerging. So it means that you will have a lot of this vaporized kind of gases which will be coming through, and you need some filter which will cut through all that, which is nothing but an IR and a UV radiation, which is being kind of bounced off by our atmosphere, which is coming from the sun. So you need to cut all that. So that's why we use a ultraviolet and infrared filter to make sure that the planets that we are imaging appear much more clearer and sharper. Okay. So that is why we use these filters. And then we have different other filters, like you have this filter here called as L Enhance and L Pro and all that. And you have another filter called as CLS. CLS stands here for city light suppression. You have a lot of lights from the city, like you have street lights, then you have lights coming from your neighborhood where they have switched on their lamps and everything. You need to cut down all that unwanted light, and you have to just always be focused on the light which you are getting from the sky. So that is why we start using these kinds of filters. Each one of them try to do a different job altogether. They cut down a certain wavelength of light and enhance a certain wavelength of light which we are interested in. So that is how the visual filters work. So, and we use it for taking pictures of the sun. We take images of the star fields, then we take images of the planets. So we use different filters. There is not one filter which will work for everything. Okay. So this is how the visual filters work. Now, when it comes to the radio filters, they are a totally different thing. So when it comes to radio filters, they are a bit different than what you saw there. Those are for visual lights, and for radio, we have to use this is a kind of a wire-wound inductor, which is also a kind of a filter. So we all in electronics, if you understand that this is an inductance kind of a filter, you use an inductor capacitor based filter, you use a resistance based filter. So you need to cut down on a certain frequency which is going to interfere in your radio listening, or when we are gathering information from a known celestial source. So you need to design and build a filter which will cut down a specific frequency or allow a certain frequency. And so you have low pass filters, high pass filters, band pass filters. They are all mostly using active components like this, either an inductor or a resistor or a capacitor. So this is how just a radio filter would look like, what I'm trying to show here. So this is a wire-wound inductor, which is also a filter. And then you use different things to analyze uh, um, the frequencies and gather the outputs and then analyze the outputs. Radio is totally different from visual. All you see on the screen are pulses like this, which I'm trying to show here, which are all, these are all radio pulses. And you try to use them and find out what is the amplitude, what is the frequency, and what is the phase shift and all that. And then you use them to correlate the data which you're getting from a celestial source. So visual is where you get straightforward picture outputs. In radio, you never get any picture output. All you get is signals like this. So it's all signals which you see on consoles, something like that. This is how the signals come. So it's all signals which come from a known radio source, and you start seeing them on your computer screen or on your console. And then you will have to start interpreting the data. Okay.
Okay. So Well, now I'd like to ask a question. Now, how do you manage to take like optical pictures from Bangalore? I mean, the skies are kind of cloudy. The atmosphere might be a big issue. So, how do you manage to do that?
Okay, when the skies are cloudy, of course, we don't take any pictures. Now, the season generally from where it is kind of clearer, the skies are clearer in Bangalore, is anywhere between mid-October till mid-March. That's the time that you get to see clear skies, and then you start taking pictures. Then you need to plan what object is there in the sky at that during those periods, and you need to do a lot of planning before you set up the equipment and then start taking pictures. So it starts through let me just show you how it all. Okay, not this. We need to do a lot of planning before we start taking pictures, and it's not that you just go there and then you can just start taking pictures. No, can I just present my screen? I'll just try to show a small snippet of what you need to do before you start taking pictures. Now this might look a bit technical, but that's how it is. Now, what we need to do before we even plan an imaging session is that we need to understand what's the sky condition. So, what is the sky that we are in? If we are in city light skies, we are anywhere between Bortle 8 to Bortle 9. Now, Bortle is a scale where it gives you what is the clarity of the sky itself. So lower the Bortle scale, better the quality of the sky. That means you can see a lot more stars and the sky is a lot more clearer. As the Bortle scale increases, that means that you have a lot of light pollution, then you have smog, then you have haze, then you have, when you have city kind of conditions, what will happen is you have tarmac roads or tarred roads. So there is always these tar roads. What will happen is during the sun times or in the morning hours, so there will be a lot of heat which these tar roads are going to take because of the vehicle movement and everything. And then a lot of heat is going to radiate up about towards the sky, and this is going to cause a lot of turbulence currents. Now, for our naked eye, these generally are not seen, but when we start taking pictures, they start appearing fuzzy. Because what we are trying to aim there is for extreme focus and extreme clarity when we are looking at star fields. So these small things are going to affect us a lot. So that is what we call as good seeing. Seeing is a term which is used in astronomy to define how good the sky is. And then we need to look for, then we need to start planning, saying that is the object that you are trying to take at the right altitude. Altitude is from the horizon. How high above is this object? Generally, it should be above 40 degrees in the city skies. And then we need to start planning on the target. And then we need to cool our equipment. We need to take the telescope out or the cameras out or the lenses out and open their front covers and make sure we cool them off at least 15 to 30 minutes so that the tube, which is the telescope, has got, it's a hollow tube and there is a air pressure, and then there is also temperature inside the tube that is different from what is outside. So both the temperature inside the tube and the ambient temperature outside needs to balance. Otherwise, you'll start getting turbulence once again. So you need to cool them off, and then you have to cool your equipment like the cameras and sensors inside the cameras. And then you need to balance the equipment, and then we have to do polar alignment. Then there are a whole list of things. Then you need to adjust to get the very sharp focus. We use a lot of other equipment called as Bahtinov mask and other things to make sure that these are very sharp in terms of focus and everything. It's not like you just go and take a picture of a mountain or a person or any object that you see on the road. When astrophotography is a totally different subject. Here I would just pause and give a comparison. When they say that in the field of photography itself, astrophotography is the niche. It means that if you take a large sample size of say 100 people who are doing photography, astrophotography will be almost 1% or almost less than that. That's because it requires a totally different kind of dedication, a lot of patience, and then a lot of understanding of the subject itself, that is astronomy itself and the science behind that, to even attempt to do them. Plus, you require a lot of specialized equipment like cameras, filters, mounts, and everything. So all of them will be, all these mounts are all controlled using computers these days. and you use something called as auto guiding. You don't use only one telescope to take pictures, you actually use two telescopes. One will be locking on to the target, and another telescope is where you actually put a main camera and start taking images. So these are things that you need to do to plan. And then based on the sky conditions, you need to start using different filters. There are certain filters which are available for you to take pictures from even from the city, but it all depends upon how much time and dedication that you can give uh, to your craft and science to actually make it happen. Sorry, that was a long answer.
Moving on, well, now, now we would like to see some of your pictures that you've taken over the course of years, well, all the years that you've been taking space astrophotographs, and well, your perspective by capturing and processing those pictures. So
Ah,
we'd like to get into that.
okay. Let me just try to share a few images. Now, this is a 6 year observation and a capture log of Saturn. Okay. Now, this also kind of tells a story, and also it gives a perspective in terms of what really happens when you start in astrophotography, and then how you evolve and what you can do with it. Now, if you start looking at the pictures in the leftmost part, where once again I try to, you're able to see the pointer here, right?
Yes, sir.
So you can see this pointer here. We are going towards something like 2019. Okay, this is almost 6 years ago. Now, the way the Saturn itself is evolving, one is that you can look at the images over the years. It's becoming sharper and sharper and sharper, right? That is observable. That means that as you start getting into astrophotography, you start with something, and then you start improving your own knowledge and then your own skill, and then you also start probably acquiring new equipment which will make things better as well. So this from the image quality point of view, you can see that clearly the image quality is getting better as the years progress. Now, what is happening to the planet? Now you can look at what is happening to the planet. The angle or the tilt of the Saturn rings when I started was around 24.4 degrees. This is the tilt, okay, where the Saturn rings are visible with a tilt angle of 24 degrees. Now, as we are evolving here, now you see this is a very, very recent image of last month, August 2024. You see the Saturn ring is almost becoming straight to our eye level, right? It's just at 3 degrees. So what you can see here is that how a planet is also changing in its orbital motion as it does a revolution around the sun. So at one point of time in say November of this year, you will actually see this 3 degree becoming 0 degree. That means the ring, the Saturn ring, will be edge on. It will just be a line which will be cutting across the planet. So that is what you're going to observe. What it means is that the whole celestial objects that you try to observe, they are not going to remain the same over a period of time that you observe. There will always be certain changes. One is this kind of a medium, an astrophotography of a medium, will allow you to observe them and then allow you to also photograph them. And then this whole fun of doing uh, capturing these images, processing these images, there's a lot of learning. And at the end of all this, the joy that you try to get is immense. You have to enjoy what you do, and you need to be passionate about all this. And then you'll understand that there's so much of change which is happening in these everyday objects that we just take it for granted. Okay, so this is one perspective of how they help, and what you learn from them, and what you learn from nature, and then what you learn from observing the sky. So that is what I have tried to mention here in the blue font, saying that I started with taking the image with a normal DSLR camera, then switched over with a planetary camera, then once again I bettered using a much better quality planetary camera, and the resolution and the imaging, of course, from the point of view of its quality increases, and in the whole part you can also observe how the planet is going to be changing in terms of its views that it's offering us to see, right? So this is what happens as part of the imaging. I was just showing one. This is of Jupiter. You can see that once again it is from 2019. till last year, November 2023. What you can observe in this image is that look at the storms or the wind storms which are happening around Jupiter's greater red spot. You can see that there was no new storm. Here you see there are new bands which starts appearing between 2020 and 2021. In 2022, you can see the band becomes very pronounced. You see, it's just like, you have an eyelid. You can imagine this as an eye, and then you have an eyelid coming on top of it. And then here in the last year picture, it becomes much more, it's much more visible. You can see, and you can see even the storms patterns. You see the storms, this pattern in the mid band here. It was kind of there. Here it started forming a storm pattern, and here you see the gas which is going around. It's a totally different kind of aerodynamics which is going on totally there, and a lot of learning about how the planetary motions and its gas, how it is moving. All these are still subject of, they don't know why it happens, and these storms move. One of them moves like this moves like this, and this moves in a different way. That means that each one of those bands, you have those storms moving in opposite directions, one of them moving clockwise and another of them moving anti-clockwise. So these are things, these are images which try to show you that how even an everyday object like a planet is having a different way of, and how it all changes from year on year. And this tries to capture and just try to show you that these are always going to change, and we need to keep them observing always. That's the kind of things that we try to learn, and this is what the images try to show you. And that is why you just keep observing, recording, and then publishing.
Okay, so sir, a small follow-up question. Now we noticed that in Saturn, we noticed that the rate at which the tilt was increasing was also increasing. What does that signify about the planet or its motion around the sun?
Oh, okay. Now, if you observe Saturn, it takes almost 29.5 years to go around the sun, one orbit. Okay. Now, why the rate of the tilt of the rings change is, you just imagine once again a cyclist. Okay, and you know what is meant by a velodrome. A velodrome is where, if you have seen the recent Olympics, what the cyclists do is they go around in a kind of a stadium which has got a bank. Okay, that is called a velodrome. Now, imagine you are an observer somewhere, you're standing right in the center or somewhere else, and then you're looking at the cyclists who are going around. When they are banking, you see a totally different view of their cycles, and the person who is riding the bicycle. So when they pass edge on, it's just like you are just looking at, when they are, it's just like a side view. Okay, and when you're looking at the side view, what will happen is that you will just see only the planet and the ring which is cutting across. Right, when it is banking, and it is banking and going across, you will be able to see a lot more of its portion on the top. You can see something called as the polar hexagon of Saturn, and then you can very clearly make out the rings and the Cassini division within the rings, the A rings, B rings, and all that you can make out. So it gives you an opportunity to study about the planet much more better in when it's trying to go through its phases. So that's what we need to know. That's a natural phenomena, as it happens as it goes through its orbit around the sun. The same way happens even for Mars. Mars, when it's nearest, when you see a picture of Mars, when it's nearest, it appears large, and you can very easily make out the polar ice caps and everything. Now Mars is quite far away, and when you take a picture, it will be a very tiny dot. So that's how things are.
Okay, so now, well, so when you take optical or radio observations, what are the main difficulties that you face while getting the pictures or getting the signal source?
Okay, in optics, when you do the optical or a visual, what we need to, it entirely depends upon uh, the quality of the sky, and what is the kind of sky that you're taking, and how clear is it. And it also depends upon the object that you're also targeting. Okay? Now there is these magnitude scales, if you understand. What it tries to tell is that how bright an object is. The brighter the object, that means that the magnitude is in the minus. So we talk about, what's the sun's magnitude? It's or the moon's magnitude. A full moon is almost minus 14. Okay? Now, when we talk about a star, which is the brightest star, Sirius, I think the magnitude is almost minus 2 something. So it is in the minus scale. So smaller the number, brighter the object is. Okay? Now, we always look at what is the magnitude of that object and how better we can resolve. Okay? There's something called as resolving power. What is resolving power? Is that if you just observe the background picture of what I tried to put there, there are many stars which are nearer to each other. Okay? If you observe, there are many stars which are nearer to each other. How well can you make out the stars which are nearer to each other and also resolve them and count their physical characteristics? So when they are in a cluster, imagine three or four stars are kind of appearing one on top of another. You should be able to resolve each one of them very clearly. Okay, so if it starts appearing fuzzy, four stars appearing fuzzy, it will be a fuzzy band of light. Or so if it is very clear, then you will be able to say that okay, it's not one star, but it is actually four stars. So this is the resolving power. Now, based on the resolving power depends partly on your equipment, partly on the clarity of the sky that day as well. So, and when you start taking pictures, there will be sky quality which will always be varying. It will not remain the same. Slight variations will be there in the night. And when you take pictures like this, what you are seeing in the background of the star fields, and this is made up of almost 6 hours of data, assume. Okay, each picture is anywhere between 3 to 5 minutes exposure. Okay? So you take almost, you can just imagine now, we take almost 100 to 120 images, okay? And then of 5 minute to 3 minute exposure, then you stack one on top of another. And then you start uh, processing that, and then you start pulling out all the information and data from it. It's a very long process. If you imagine that 40% is all you use your telescope and your cameras to do the actual imaging, 60% of the time is spent in post processing. So that's the kind of activity which requires, because this base image will be almost anywhere between 7 to 8 GB of data, and you need to once again work on it. You need to resolve them. You need to see that there are bad frames which would have come. You need to kind of throw them out. Or sometimes you have satellites which come, or sometimes you have birds which will interfere. Sometimes you have airplanes which will interfere in images. To throw them all out and take only the good ones. So that's the whole way of trying to integrate, stack them, and then use only the good images.
No wonder, well, the background looks so pretty. Well, do you have some more images that we can look at?
Yes, I'll just try to show you just a second. Let me open that. You saw a couple of the planetary images. Now I'll try to show you the images of the deep sky. Hold on. Just a second, I'm opening them. It takes a couple of minutes. Please bear with me.
Yes. So now, while it's opening, I
Yeah.
had a, so you said that you use the resolving power of the camera to identify individual stars in a star cluster.
Yeah.
So about not recently when it was discovered. No, it was recently discovered in 2020. The Stephenson 2 star cluster.
Mm-hmm.
There are multiple stars in there, and one of them is speculated to be the largest star in the known universe.
Mm-hmm.
So how do you? So what kind of cameras did they use to actually identify the stars, or how did they manage to determine the weight of a particular star in the star cluster?
Okay. Now, a short answer is very simple like this. Now, the density of the star determines that how big the star is and what does it contain. When I meant density here, is that what is the kind of gas, or what is the kind of medium that it is packed in a kind of a square meter area. Okay. Now, if you imagine the sun, you know what the sun is made up of. It is hydrogen getting converted into helium, isn't it?
Yes.
Okay. The same way, how do you know that what the star contains? Now, the starlight which comes and you pass this through equipment like a spectroscope, what it will do is that this equipment spectroscope, this light which is coming, it splits. And from the splitting of the light, it's just like passing the sunbeam into a prism, and you get a Webb-Guiard spectrum. So from there, you can find out what is the elements which this star is made up of. Because I was trying to tell you that each one of these elements have a very clear color, like the hydrogen gas when it's split. It gives you a yellow, a pinkish and a red color tinge. And oxygen is kind of bluish, and then you have sulfur, which is kind of once again yellowish. Now, when you have all this, you can make out that density of the gas, and also what is the amount of these combinations or concoction that the star has. So they get into a science called a spectrometry or spectroscopy, which tells them a lot more about the stars. And the stars and their spectroscopy is not limited only to visible light. They also go into say the X-ray spectrum, then they go into the gamma ray spectrum and all that. Like say for example, the Aditya, which is studying the sun now, which ISRO has launched almost year and a half back. It is also looking at the sun in other wavelengths like X-ray and gamma ray and all that. Okay. So these kind of equipments tell you what the makeup of the star is. Based on a certain value of the makeup, you can tell that how big the star will be and how much the mass is, how dense it is. It's just like analyzing something in your blood and trying to tell what is your age, which you can do these days, I think, and what is the DNA that you are made up of. And that the same way, by looking at the starlight, you can make up and tell that what the star is made up of, what is its age, and in what part of the celestial life cycle it is. And you can do a lot of things there. That's another set of science. Okay.
Okay.
Now, these are few images which I'm just trying to show. This is once again, this is the core of the Milky Way on the left side, and this is called as the Thor's Helmet Nebula. Okay, so this is, I'm just trying to give even the light years there, and then, if you look at this Thor's Helmet Nebula, there is a star here called as Wolf-Rayet star. So, and that star is kind of exploded. This is a supernova. It means that the star has gone kaput. Its life cycle is complete. When it dies, it just dies a very violent death, and it ejects all the interstellar matter in a particular way. And this explosion, like a bomb going off, is what is shown here as a Thor's Helmet Nebula. So these are kind of nebulas. These are pictures that are taken from here. And this once again, there's a different. One of them is a Cedar region. This is part of a constellation of Cygnus, and it shows many objects here. Like this is called as the Crescent Nebula. This is Crescent Nebula. This is all this nebulosity, all this red color is coming majorly from hydrogen. Okay. And here, this is a very well-known nebula called as Orion, where you can see the colors here. Each color is different, and each color tells what is this made up of. Like I was talking about hydrogen, which is reddish and pinkish tinge, and then you have the blue, which is coming from the oxygen, and then the yellowish tinge coming from sulfur. All this is shown when you start taking pictures like this. This is once again a different picture. This picture is about you have the lagoon and the Trifid Nebula there. The bluish tinge is the Trifid Nebula, and then you have this is the Pleiades. This is a reflection nebula. It means that the stars are so bright that there are interstellar clouds passing, and these stars are behind the clouds. It's just like when the sun is behind the cloud, it illuminates even the cloud, and that's exactly what a reflection nebula is. So this is an emission nebula. That means these colors are emitted by the stars, and its hydrogen generally is like that, and they are emitting itself. Here, a star is brighter, and it is reflecting light with the interstellar cloud which is passing in front. So these are pictures, some of them which I've taken from here. Once again, this is another picture of a different one, which is called as the Eagle Nebula, and then a Flame Nebula. So it just appears like a flame, a wicker flame of a old kind of a lantern light. So that's why it's called as the Flame Nebula. This is called as an Eagle Nebula. It appears like as an eagle, and it is also called as the Pillars of Creation. So this is one of the famous photographs taken by Hubble as well, where all these nebulas are stellar nurseries, which means that new stars are born from these nebulotic clouds. All that small tiny dots that you're seeing is actually new stars which are born. And stellar life cycle is a very, very interesting subject, where molecular clouds like hydrogen, what will happen is that they collapse due to gravity over a period of time, and they compress, and they start forming new stars. So this is a Helix Nebula. It is called as a planetary nebula, which is nothing but, if you see a faint star here, this is also called supernova. That means that it's died, and during the process of death, it's all ejected all its outer mass, and that's how it looks when you see them or capture them. This is like a horse head nebula. This is called as a diffusion nebula, where this is just a nebulotic cloud which is just risen up, and it looks like a horse head. So that's why it's called as a horse head nebula. You can see all the dense mass of cloud, which is all hydrogen once again. Yeah, this is once again North America and Pelican Nebula. You can imagine this looks like the shape of a North America map of North America, and this vaguely represents a pelican, a bird. So that's why it's called as a Pelican Nebula. This is called as a Seagull Nebula. It looks like a bird, a seagull, and that's why it's called as a Seagull Nebula. So I'm just giving a comparison of how far they are in terms of light years. So these nebulas are totally different. They are very colorful to look at. Yeah, this is in Gemini. You will in the constellation of Gemini, you will see this is called as a jellyfish nebula. It appears as a jellyfish, and then you have M35 star cluster, and this is appearing as a monkey head. I'll show you a better picture of this. So there's a Christmas tree. This looks like a Christmas tree, or it is also called as a fox fir. It appears as a tail of the fox. It's just like a tail of a fox. And this looks like a rose, and that's why it's called as a Rosette Nebula, or a rose in the sky. So these are a few pictures. It goes on and on. It all depends upon how long you want me to show. There are hundreds of them. This is once again a Rosette Nebula. It's much more. I try to zoom and try to take a bit more nearer or resolution of that. This is how the rose in the sky looks like. It's called as a Rosette Nebula. Now you can see this is called as a skull and a crossbone nebula. Or if you look at this picture, it appears as an ape. You have to do a lot of imagination. This is the eye of the ape, one eye and the other eye. This is the nose, and this is the mouth, and this is the mane of the ape. So that is why it is also called as the ape, or the skull and crossbones nebula. They have funny names for all this. Yeah, this is once again the cloud inside Rho Ophiuchus. So it's Antares. This is in the constellation of Scorpio. You can see the main star Antares, and then this is the Crab Nebula. It's a very famous nebula, M1, or as it is called as. This is once again a star which is finished its life cycle, and it's in the supernova. It means it's just ejected all its mass, and it's just like a time bomb which is just blasted, and all that ripples have come out. And there's the main star which is just faced its death, this small dot there. So let me know if I have to continue, or I have a lot of pictures that I can keep on going. This is the Monkey Head Nebula. Once again, you can see and then the Rosette Nebula, the core of the Rosette Nebula. I'll just show you all the small tiny dots that you see. These are all the new stars which are born. So what I'm trying to say is that if somebody has taken a picture of this one, say 100 years ago or something, you might have not seen these dots. So these dots have appeared because new stars were born which were not there some 100 years back. So that's how things are changing in the sky, and they keep recording them. And once again, each one of them is a different nebula, and each one of them gives you a different perspective, and we can go on and on and on. So these are pictures of the nebula. Then there are star clusters. So then there are galaxies. Then there are so many other things. But yeah, I don't know how we are doing on time.
Well, we were fine on time. Well, yes, that was definitely spectacular. Well, now looking at all those nebulas and stuff. Well, but since they're supernovas, I mean, they are blowing away from a certain spot from where they exploded. So, in future, will there be a time when people won't be able to see these nebulas together because they've dissipated too much?
Okay, you mean a supernova today which can dissipate? Well, they are there. When I talk about the M1 star cluster, which I showed, the Crab Nebula, the supernova of that was seen and recorded by the Chinese in somewhere 980. Okay, you can just imagine for the last 1,100 years, you're still seeing them. A lot more generations are going to enjoy, and a lot more stars are going to explode. So it means new supernovas are going to get created, and they are as we speak now. A lot more are getting discovered as well. Okay, supernova observation and supernova hunting itself is a great field of exploration which the professional astronomers are involved in. So there will be a lot more to enjoy.
That seems so well. Before wrapping up, I'd like to ask a final question, which has been on my head for a long time. Well, now you've been doing this astronomy work for a long time now. You have a really vast amount of knowledge when compared to all of us, all the students and everyone. So I'd like to gain your perspective on how a normal college student or a group of students should actually go about getting these images, and how should they proceed? In which direction should they proceed?
Yeah, it's a very nice question and a very important one as well. Good that you asked it. Now, if you just imagine that you have to start taking pictures, correct? So one of the fundamental things to do is to understand where are these objects in the sky. Sky is a very vast area, right? And if you have to say that I'll have to find the crab supernova or M1 cluster. Uh, so how do you figure that out? How do you find them? Hmm? Now, for that, you have to know the constellations. Constellations are nothing but star patterns. There are so many stars in the sky, and how do you make out where am I looking at? Okay, how do I identify? Now, the constellations are not that difficult. There are almost 88 constellations by IAU now. IAU stands for International Astronomical Union. So it's an international body which is involved in standardization and normalization of all the astronomy. And once you know these 88 constellations, and within these constellations lie all these objects. Okay, like say within the constellation of Gemini is where you find the jellyfish nebula, okay, or the monkey head nebula. No, first you need to find out where is Gemini, okay, and then you need to understand what all stars make up the constellation of Gemini, okay, and then it is easy for you to understand that at the foot of one of the Gemini constellation is where you find this monkey head nebula. So then you will know that okay, I have to look at that pattern in the sky there, and then I have to follow this star field pattern. And when I follow this star field pattern at a specific place next to a specific star or a cluster of stars or whatever you can call it as a landmark, and then you can find out and figure out that this is where it is. Then you start pointing your telescope or your camera to that place. Only then will you be able to take images of that. Okay. Now, imaging is also not like just you take a camera and it's not like you just take a camera and you see an animal going there, you start taking pictures. No, and stars and star fields are very, very, very faint objects. That means you need to keep the camera still for hours and hours and hours, compensate on the Earth's rotation around its own axis because the stars keep moving. That is because the Earth is moving, right? And then you have to compensate. That means that if you have seen any star in the telescope, it will not stay within the field of view for a very long period of time. Within a minute, it would have vanished unless your telescope has got an active tracking mechanism where it will keep the star in focus. So you need to have specific or specialized equipment called as the mounts, which are computerized once again. And then you need to have filters and all others. Then you start taking pictures. So it's a process, and there is no shortcut for that, unfortunately.
Okay, so now we are at the end of our podcast. We'd like to thank Ramohan sir for giving us your time and showing us the beautiful pictures and also giving us insights into how the radio observation works and optical. So we'd like to wrap up now. Thank you, sir, for your time. It was a
Thank
pleasure.
you. Hope it was all useful. Thank you, and good day to you all.
Yes, sir, it's definitely useful.